because it's not ready yet. There's nothing to pick yet.
Okay, so this is the given problem. As you can see, the matrix is 1, minus 1, 4, 3, 2, minus 1, 2, 1, minus 1. And I'm going to give you that the eigenvalues are 1, minus 2, and 3. So already I made the problem easier because I told you what the eigenvalues were to start with. Alright, so how do we find eigenvectors now that we already know the eigenvalues are this, this, and this? Okay, so what we have to look at is, for example, a minus I. We want to find the null space of that, basically, so that a minus I is what? 0, minus 1, 4, 3, 1, minus 1, 2, 1, minus 2. Alright, so then we can do row reduction here, and we get to 0, minus 1, 4, 3, 0, 3, 2, 0, 2. So that's row 2 plus row 1. And this one was row 3 plus row 1. Let's see here. And at that point, you can see that the third and the second equation, the same equation, and the first equation separate. So if you let UVW be an element of the null space of A minus I, you can see that we have to have the following equations. We've got minus V plus 4W equals to 0, and we've got U plus W equal to 0. So I can use W as a parameter. So basically just set W to be 1. Let's see here, so that gives me V is equal to 4W. This tells me U is equal to minus W. So in short, I can use, let's see here, minus 1, 4, 1 is a good eigenvector with eigenvalue 1. There we go. So that'll be part of my eigenbasis. So there we go, lambda 1 equals to 1. That one's done. Next, I will go on to do the next eigenvalue. Let's see here. Lambda 2 equals to minus 2. So there I've got to look at a plus 2i. So a plus 2i would be 3, minus 1, 4, 3, 4, minus 1, 2, 1, and 1. I do some row reductions. I won't tell you which ones, they're going to be obvious from what I do. I guess I'll tell you. I multiplied the first row by 2. I multiplied the second row by 2. I multiplied the third row by 3. And then we can clear out under that first pivot position by subtracting the first row from the second and third row. And that gives us 6 minus 2, 8, 0, 0, 10, minus 10, 5, minus 5. Okay, so again, at this point I don't need to do any more row reductions. I can already see that the last two equations are really redundant. They're the same equation, and maybe the first one is genuinely different. So let's see here. So basically from these I can glean that, well, I mean, the last one would be literally 5v minus 5w equal to 0. So I would take from that v is equal to w. And then the first equation, I'll pick on down here, would be 6u minus 2v plus 8w equals to 0, of course, Ming style. And but since v is equal to w, I can trade this v for w, and I get 6u. Let's see here. V was w, right? So it's plus 6w. So therefore u is equal to minus w. Again, I can use w as a parameter here, and so I find that in particular choose choose w equals to 1, we get minus 1, 1, 1, an element of the null space of a plus 2i. So there you go. There's our second eigenvector corresponding to eigenvalue minus 2. And then finally, excuse me, find the right color here, maybe orange. Sure, I'm still in frame. Alright, so so finally we have lambda 3 equals to 3. So I gotta look at a minus 3i, which is, by the way, what? This marker's not working. A minus 3i is, let's see here, minus 2, minus 1, 4, 3, minus 1, minus 1, 2, 1, minus 4. So again, I will just be rather unimaginative and make the first columns all match up by multiplying by 3, 2, and 3 respectively. That gives me minus 6, 6, 6 in the first column. And I've got minus 3, minus 2, 3, 12, minus 2, minus 12. And then clear out the first row again. Hopefully that will be successful again. Minus 6, minus 3, 12, top row, that stays the same. Got myself 0, a 0, minus 5, 10, and 0, 0. Aha! Well, this time you can see that this tells us that I'm going to divide by 5, so that tells me minus v plus 2w equals to 0. So therefore v is equal to 2w. Looks like we'll be using w as a parameter again. There are other problems where w can't be used as a parameter because it has to be 0 or something. That just hasn't been the case in this problem. It's just it's a quirk of this example. See here, so going back, I'm going to go back to that equation. Minus 2u minus v plus 4w equals to 0. But we just found out that v was 2w, so this is minus 2u minus 2w plus 4w, which is equal to minus 2u plus 2w. So consequently, we learned that u is equal to w. Aha! So what we find then is that setting, again, just choose w equals to 1 because I can. We're just looking for a representative basis element for the null space. We don't have to find all of them necessarily at the moment. So what I got here is I got a 1, I got a 2 from that, and I got a 1 again. That's an element of the null space of a minus 3i.
Oh, I don't want an orange.
Woohoo! Alright. Now, put that up a little bit. So what is our conclusion? Our conclusion is that, thus, if we use beta equals to, let's say, minus 1, 4, 1, comma, minus 1, 1, 1, comma, 1, 2, 1. This is an eigenbasis for A, and it's a basis of eigenvectors. And if we calculate this similarity transformation, we know from the theory we discussed, even without doing the multiplication here, that what we're going to get is a diagonal matrix with a 1 here, a minus 2 here, and a 3 here. And that's part of the wonder and beauty of the eigenbasis. So there's one example. I hope you see that this was slightly more complicated than ones we did in class, but it's again just a null space calculation, alright? So that's page 1. Let me do another one here that's a little bit simpler. So our next example, let's see here. Let's see if we can guess the eigenvectors for A below. Alright, so if we can do that, then I can calculate the characteristic polynomial directly. So let's see here. Suppose A is equal to
Okay, I need to pick one.
So 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1. So this is a relatively simple matrix. It's not quite diagonal, right? But it's almost diagonal. So given the example we did in class with the diagonals, you should be able to immediately guess that there are two easy eigenvectors defined here, right? Because you can see from this that A times E1 is equal to E1 again, right? So therefore E1, which is, 1, 0, 0, 0, is eigenvector with eigenvalue lambda 1 equals to 1. On the other hand, we can also see that AE2 is 2E2, so therefore, E2, which I won't write out, you know what it is eigenvector with lambda 2 equals to 2. Now, how did I see that? Just by looking at it, and I know matrix multiplication, so great. Now, let's see here. These guys, I can also, maybe you can't, but I can at least. So if I look at this, I'm looking for eigenvectors associated somehow with this block down here. You can try it out. Let's see here, let's do it. What if I do 0, 0, 1, 1, 1, what would happen? So I'd have 1, 0, 0, 2, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1. Okay, do this multiplication, what do I get? I get 0. I get 0. 1 plus 1 is 2, 1 plus 1 is 2. Well, check it out. So I got another eigenvector with eigenvalue 2, right? So let's see, what is that? That's, there you go. So apparently, again, let's say lambda 3 is equal to 2. Sometimes we might say lambda 2 is equal to 2, it's repeated. We have two different eigenvectors for it. All right, fine. Now, one of the other things you should have been able to expect from the very beginning with this matrix, because this matrix has a repeated row, right, third and the fourth rows are the same, you can immediately tell this matrix is not invertible, and therefore must have 0 as an eigenvalue. In particular, let's see here, how about this one? 0, 0, 1, minus 1. That'll be in the null space of A, because if you multiply that, what you're going to get, right, I won't write it out, you can see it. So you get 0, 0, change that to minus 1, you get 1 minus 1, 1 minus 1, so you get 0 and 0. So therefore, the fourth eigenvalue, or the third, depending on how you want to count, is 0. And, okay, so, by the way, we can also see that the characteristic polynomial for this guy would be, well, let's see here, it would be lambda minus 1 times lambda minus 2 quantity squared times lambda. That's because if we have an eigenvector, that means there's at least one copy of lambda minus the eigenvalue in the characteristic polynomial, right? Or if there's 2, there has to be at least 2, because we proved that 1 was less than or equal to the dimension of E lambda was less than or equal to m. So I just found that for lambda equals to 2, this is 2, so that forces this to be at least 2. But this is a 4 by 4 matrix, so it has to look like this. That's the characteristic polynomial. And if you were to calculate the determinant of A minus lambda I, you'd verify that very quickly. It wouldn't be hard. In fact, I'll do it. Right, because that's the determinant of 1 minus lambda, 0, 0, 2 minus lambda. Again, I don't need to do this because I just told you other reasons for it, but here it is. Lambda, 1 minus lambda. Oh, Matthew's on the scene. Let's see here, 0, 0. And so that gives me the determinant of the blocks. Right, which is what? That's, of course, lambda minus 1 times lambda minus 2, and this guy is lambda minus 1 quantity squared minus 1, which works out to lambda minus 2 times lambda So this picks up a square and you get the lambda, and there you go. So my point here is, yes, sometimes problems are complicated enough that you have to work out the null space calculation like our previous example, right? But if the matrix is simple enough, maybe you can just look at the matrix and see what the eigenvectors are if you just take a second to think about it. So if I was wanting to just look at it and tell me, I would probably say something like, by inspection, tell me what the eigenvectors are of this matrix. I realize it's kind of a mean question because I'm asking you to guess something, but inspection is an important idea in math that you should be aware of. We don't always have to work everything out if we can just see it. On the other hand, I don't think I could, by inspection, see that the eigenvector of that was -141 or -111 or even 121. Like, I can't see by inspection, right? So in that case, I have to calculate. I have no option. So I just wanted to mention this to you guys. These ideas I haven't focused much on. Anyway, I'm going to stop there for now.